At the end of last time, we were specializing to the case of two-electron systems. And so this is in part because we're going to be doing the helium atom one more time. And in part as a warm-up for multi-electron systems, which are more complicated. But so in general, we can write the state, and I'm going to be writing it very schematically to start, as some linear combination, which I put a summation sign for, over the spin parts of the wave function, or the spin parts of the state, tensor product with the spatial parts. Okay, and last time we talked about the fact that the spins we can write as a linear combination of the following things. So first of all, there's a spin 0 part. Okay, and we called that chi00, so it's a ket. And it has spin 0, and then of course that means that the z component has to be 0. And it's anti-symmetric, because if I just interchange the first arrow with the second arrow, I get a minus sign. Okay, and then there's chi11, which is when they're both up arrow. Okay, and that's a total spin 1, z component is 1. And there's chi10, which is 1 over root 2, up arrow, down arrow, plus down arrow, up arrow. That's spin, total spin 1, z component 0. And then there's chi1 minus 1, which is when they're both down. Okay, and those are all symmetric. So according to our postulate or theorem that tells us that two fermions, two identical fermions, in this case electrons, have to be totally anti-symmetric, then if we look at the spatial part, one way to specify what the spatial part is in terms of wave functions. Okay, and there will be 4 of them, because we can label them by the total spin and the m sub s. And we see from over here that there's 4 different combinations that we can have. And so if we have a wave function that depends on the spatial coordinates of the 2 electrons, that we can write as usual, the matrix element of the position eigenstates with the spatial part. Okay, and so I want to emphasize there's a different one of these, a different wave function for each spin combination. So for each s and m sub s. And they have to obey the correct symmetrization or anti-symmetrization properties. So my wave function that I'm labeling by total spin s and m sub s, the wave functions themselves aren't carrying the spin. They're correlated with the spin over here that they're multiplied by. But they still carry that label because you have to know which one goes with which. So this one obeys that if I interchange the 2 coordinates, I get either plus or minus sign multiplying them. And the plus is for spin 0. And the minus is anti-symmetric for spin 1. And it has to be anti-symmetric because the spin part was symmetric. Okay, so now what do you do with these wave functions? One thing you can do is ask what's the probability to find an electron somewhere. So if we go back to the postulates of quantum mechanics and apply it carefully to these tensor products, then we can say that the way things work is that the probability to find electrons, both of them, at different split places. So let's say within some infinitesimal volume D3R1 and another one within infinitesimal volume D3R2 is equal to, so it's a differential probability because those are infinitesimally small volumes. And what we do is we sum over the spin and the z component of the spin. We multiply by the infinitesimal volumes. Okay, multiplied by the wave function for that spin combination squared. Okay, so the idea here is, let's say I choose my origin there, and then I draw a little infinitesimal box of volume D3R1 at the position R1. And then I draw a different infinitesimal box here. That's D3R2 at a distance R2. And so what I'm doing is I'm saying, what's the probability to find both an electron in this box and an electron in this box at the same time? And that's what this expression is giving us. So if you want to find the probability for some volume, you're going to have to integrate with respect to D3R1 and or D3R2, which we will do a little bit later. Okay, but we can, just another way of writing this is we can take the differentials, of course, outside the sum. And then we're summing over s equals 0 to 1, because for 2 electrons, those are the only combinations. And m sub s is minus s up to s. Okay, and then we're taking the square of our 4 different wave functions. Okay, any questions on this so far? All right, so now we're going to be temporarily making a big assumption. And the big assumption is really, if you think about it, not very well justified. But we're going to assume that we can ignore the interaction between the electrons. So suppose we ignore the interaction between electrons. That might seem crazy because electrons carry negative charges, and so they repel each other. And so we're just ignoring that. But one reason we can get away with it is because we're typically interested in, for example, the situation where we have a nucleus, which has a much larger charge. And so that's the main effect that's causing the energy levels or the wave functions of the system. And we're going to treat the interaction between the electrons as a small perturbation, even though it's a rather large repulsive effect. So in any case, our Hamiltonian under this assumption is, remember, it has to be symmetric under interchange of our 2 labels. So it's going to look something like this. I'm not including an interaction that goes like R1 minus R2, even though it's there. So maybe I should call this my unperturbed Hamiltonian. Okay, and then we want to find the eigenstates of this. So we would solve the Schrodinger equation, and we would write this as minus h bar squared over 2m, Laplacian 1 squared, minus the same thing for Laplacian 2 squared. So that just means Laplacian with respect to the coordinates 1 and 2 respectively, plus the potential for R1 plus the potential for R2. Now I'm writing them not as operators, but as coordinates, because I'm doing now this in position space. Okay, and I'm leaving off the spin labels temporarily. And that has to equal the energy eigenvalue. Let me call it an unperturbed energy eigenvalue. So we usually have been calling that curly E times psi. Okay, now I'm not going to be specific about what my potentials are at this point. We just assume there is some potential, and we also assume that we can solve this equation. And one way we can solve it is by the strategy of divide and conquer, which is we can just ignore R2 and solve it for R1, and then vice versa. So let's say we've done that. Let me call phi with a subscript for curly e be the wave function solution for a single particle. So this is the wave function solution to just the single particle Schrodinger equation. So I don't need a subscript, I guess, on my Laplacian. Nor do I need a label on my potential, because this is just the definition, the equation that defines my single particle wave function. Okay, and so the idea is if I can solve that equation, if I can solve this, then I just multiply any two of them together and it will solve this differential equation. The key thing being that there's no potential that mixes up the two coordinates. Okay, so that will mean that we have the following unperturbed energy eigenstates. So I'll write unperturbed here. Energy eigenstates. And their energies are just going to be the sum of, let me call them A and B. I choose any two solutions, and I'm going to have a wave function, for example, for spin 0. Which I get by symmetrizing my two individual one particle wave functions. So I'm going to put a 1 over square root of 2. I have my wave function for energy A, which I assign to coordinate 1, and for energy B, which I assign to coordinate 2. But then I'm told that this thing has to be symmetric, so I have to add to that the same thing, but with the spatial coordinates interchanged. That will make it symmetric. And it's really the only way I can make it symmetric. And then I include the 1 over root 2 to make it be normalized in the right way. Okay, and so this is for the spin singlet. But I could also have the spin 1, and so this has 3 different values of m sub s. In all cases, this thing is a solution. And I just do the exact same thing, but I put a minus sign. Okay, and that's for the spin triplet. And because I'm assuming that there's no interaction between the electrons temporarily, all 4 of these wave functions are degenerate in energy. So there's a full 4-fold energy degeneracy. Okay, so for each of these possibilities, we can consider the probability, as we mentioned above, to find an electron within volume D3R1 near R1, and another electron within D3R2 near R2. Okay, and that's equal to, as we said, D3R1, D3R2. We're just considering one spin combination at a time now, though. And so when we write down our wave function squared, okay, now we can plug in what we got here. Okay, and I'm just going to do it, and then I'm going to put plus or minus so I don't have to rewrite everything multiple times. Okay, and so when I square the 1 over square root of 2, I'm of course going to get a 1/2. And then I get the following terms when I take the complex square. There's going to be wave function for EA, R1, times wave function for EB, R2. And then I get the same thing in reverse. Okay, but then I get the cross terms, which are going to come about from this times that. Okay, and one of the cross terms is going to be the complex conjugate of the other. And so what we will get is plus or minus, plus if it's spin 0, minus if it's spin 1, 2 times the real part. And the cross term is 5 for EA of R1, 5 for EB of R2. But that one's complex conjugated, multiplied by phi for EB, R1, phi for EB, R2, again, complex conjugated. Okay, and plus means total spin is 0, minus means total spin is 1. Okay, now one thing to notice is that for either one of the spins, this probability density is invariant. So note for either spin, this is invariant under interchange of the 2 electron labels. So that's the way it had to be. We said before that our answers to physical questions could not depend on what we chose our labels to be for identical particles. And that's true. It comes out the same either way. When I interchange R1 and R2, that basically this term turns into that term, and this term turns into itself. Okay, regardless of whether this is a plus or a minus sign. And the real reason for that is even though the wave function flips sign for the spin 1 case, we're squaring it. And so when we square it, it doesn't change sign. And that's why the probability, which is the answer to a physical question, is something that doesn't depend on the label R1 versus R2. Okay, on the other hand, this term is a non-trivial plus or minus. And so that term is known as the exchange density. Okay, it's a change in the density that comes about from the fact that the 2 parts of the wave function can interfere. And we notice that if it's a minus sign, that's the spin triplet. So when the electrons are in a spin 1 state, okay, the triplet, they avoid each other. That's what this is telling us. So what do we mean when we say they avoid each other? We notice that if you plug in that E sub A and E sub B are the same thing, and you just look at this plus that, it's exactly canceled by minus 2 times this, because this works out to be the same thing as either one of these two terms separately in the case where EA equals EB. Okay, so that means the probability is 0, or the probability density, when R1 is equal to R2, and they're in the same state. And these states, these wave functions are continuous. And if we make the rather mild assumption that they're smoothly continuous, that means that if it's equal to 0 when R1 is equal to R2, then it has to be small when R2 is close to R2. So by continuity, without even committing to a particular set of wave functions, they will be small when R1 is close to R2. Okay, now on the other hand, the exact opposite happens if it's a spin 1 state, because then I get a +2 here. And if if the phi's are all the same, then I've got 1 + 1 + 2. And so it's 4 times as big as it would be perhaps naively. So when in the spin equals 0 state, okay, they attract. I'll put attract in quotes. So here they repel in quotes. And I want to emphasize this has nothing to do with the electrostatic repulsion between electrons or any other electrical properties that they have. This would happen even if they were particles that didn't have any charge whatsoever. They attract in the sense that there's an enhanced probability to find them close together. Probability for R1 approximately equal to R2 when they're in a spin state and the other states are the same. Okay, so looking ahead a little bit, now suppose we actually do include the electrostatic repulsion between the electrons as a perturbation on top of what we're already doing. So what does that mean? That means the S equals 0 state here is going to have the electrons close together where they're trying to repel each other, and therefore they have a higher potential energy. So these S equals 0 states are actually going to be pushed up in energy compared to the S equals 1 states, where the electrons are, that this exchange degeneracy is trying to keep them far apart, and they want to be far apart because their electrostatic repulsion is going to push them apart. So we'll actually come back to that again when we talk about the details of the helium atom. All right, but before we do that, let's answer or address a sort of a strange feature of all this, which is we believe that all electrons in the universe are identical. And so an electron that's on Earth is the same sort of particle. It's an identical particle to the electrons on Pluto. And so you might ask, well, why don't we have to take into account interactions of this type between electrons on Earth and on Pluto? Or I think in the notes I called it Antarctica and Batavia or something like that. Let's call it in class, let's call it DeKalb and Batavia. So let's consider the fact that electrons in DeKalb are identical to electrons at Fermilab, and figure out why it is that in everyday life we don't have to worry about this. Okay, so the question we're going to address is, why don't we need to worry about the exchange degeneracy between very distant electrons? Because it looks like there's this big minus sign or plus sign depending on the spin state And therefore, you might think the spins are going to cause correlations that are very large between distant electrons. So exchange degeneracy for distant electrons. Okay, so the idea is, suppose that we have an electron here in DeKalb, or wherever you happen to be at the moment. And so it has some single particle wave function, which I'm going to call phi sub d. And there's a single particle wave function for some electron that's localized in Batavia.
I'm sorry, Professor.
Which
Sorry
is,
to interrupt you. The last word in the second line, is that exchange degeneracy?
yeah, it's not spelled right, is it?
Oh, I'm sorry. No, I had a hard time reading it. Okay, thank you.
I'll rewrite it. Okay, so the key thing is that what we're going to do is we're going to suppose that they have no overlap, or that their overlap is very small. Now, one way this could happen, of course, is because they might have nuclei. And so when you find the unperturbed states, one of them is near a proton in DeKalb and the other one's near a proton in Batavia, but we don't have to worry about whether that's the reason or there's some other reason. But what no overlap means is just that if I take their product, that's very close to zero, always. Okay, and in such a way that, and this is the reason for the labels, is if I look at the DeKalb wave function, that's supposed to be non-zero only for R in DeKalb, and similarly for the Batavia one. Now, these are approximations, but we're assuming that these are very good approximations. Okay, so now let's write down the total wave function, allowing for the different spin states that they could be in. So the total wave function for our 2-electron system is, as we already wrote before. Okay, I just take my product of wave functions, and then I do plus or minus the same thing, but their roles are reversed. This is what makes it might look like there would be a big effect of exchange degeneracy that we have to worry about. Okay, and we do that for each, I haven't put the spin labels on the left, but for each S and M sub S with the plus or minus sign accordingly. And now what we do is we say, okay, what's the probability of just, now we're just going to ask about one of the electrons. We're just going to say, I'm at some position. What's the probability that I see one electron near me? So I say, what is the probability of seeing an electron? I don't care which one, because after all, I can't tell the difference anyway between indistinguishable electrons within D3R of R. Okay, so the answer to that question is what I should do is I should first ask, what's the probability of seeing the electron that I labeled 1 near me? And then what's the probability that I see the electron 2 near me, and add them together. So the answer is going to be, it's going to be proportional to the size of the little box that I'm asking about. And then there's a probability density. Okay, and it's going to be D3R integrate over label R2 of this wave function. That's supposed to be a comma, not a 1. So let me write down the whole thing and then I'll comment on the individual parts of it. Okay, so I've just written down the previous thing, but now I'm calling in the first term, I'm calling R1 to be the position I'm interested in. And since I'm only asking about one electron, then I'm integrating over the position, all the possible positions of the other electron, and then the opposite in the second term. So the interpretation of this first term is, this is the probability that electron 1 is the one I'm finding at R, summed over all possible electron 2 positions. Okay, and then the interpretation of this term is that that is the same thing except with the roles reversed. And the sum of those should be the probability that I find either one of the electrons at the place that I'm worried about. So notice that when I'm summing over the electrons, I'm really doing an integral. And so if I just now ask about the probability density, we can go ahead and do those integrals. So on the first term, since I'm only integrating over R2, I can just pick out the dependence on R1 and pull it out of the integral sign. And notice I'm dropping the D3R everywhere because I just want the probability density.
Professor?
Yes.
So the R is not a vector?
Oh, I left my harpoons off some of these. Sorry, got in a hurry. Yes, they're all vectors. Thank you.
Thank you.
Okay, so the probability of finding an electron, probability density of finding an electron near R is going to be from the first term. My wave function that I'm calling my DeKalb wave function times integral D3 R. I guess I'll keep my label here. Okay, but we've normalized our wave functions presumably, so this is just 1. Okay, and then the same thing for now my Batavia wave function. This is by plugging in this stuff right here. Okay, and this is going to be D3R1 phi DeKalb R1 squared, but it doesn't matter because the whole thing is just going to give 1. And then there's going to be the cross term. Okay, and that's phi DeKalb R, phi Batavia R. And then I need to integrate over the rest of this stuff. And I guess I'm supposed to put, I'm putting my complex conjugation marks here. Let's see. This should have actually been a DeKalb label. And this is a Batavia label. But none of this matters. Because now the point is that when I multiply together the two wave functions, according to this up here, I always get something that's 0, or in reality, extremely small, exponentially small. So not only is this 0, approximately, but this is also approximately 0. I guess I can just write that here. So this thing is doubly 0. And so we can just ignore the cross terms, right? And so the probability density of observing an electron somewhere separates into two parts. There's the DeKalb part squared, plus there's the Batavia part squared. Okay, and the key point is that only one of these is non-zero for any fixed r. And so if I'm asking questions about what's the probability to see an electron here or there or somewhere else, it just separates. The separability is what means that we can ignore, when we're doing experiments in DeKalb, we can ignore what's going on in Batavia and vice versa. Okay, so another way of writing that is, if I draw a little domain here for DeKalb, and another little domain here for Batavia, right? And if I draw vectors from here to here and here to here, okay, my probability density at any given point is one or the other. So it's either phi DeKalb squared if in DeKalb, because then the other one doesn't contribute, or it's phi Batavia squared if in Batavia. And wherever I am, I don't have to worry about the other term because it's just non-zero. I'm sorry, because it's just 0. Okay, so the problem decouples into separate ones. If my wave functions are sufficiently separated. And that means if my electrons are sufficiently separated. So that's despite the fact that the wave function itself has this exchange degeneracy part, or exchange part. The answers to things like probabilities don't have that. Okay, questions about that? All right, so we're going to come back to the n equals 2 case again. Probably in the next lecture is when we're going to redo helium. But let's consider graduating now to n identical electrons.
I'm sorry, Professor.
Yes.
Can you scroll up just a tad bit? Thank you.
Do you have a question about something here?
I'm sorry, no, I was just behind.
Okay. So let's consider n identical particles. Actually, we won't assume they're electrons for a while. And let's put them in a potential. For electrons, this would be a nuclear Coulomb potential. And so we're going to assume our potential is going to give them bound states. And suppose the single particle wave functions are therefore discrete. Actually, if they are bound states, they will be discrete. So they have wave functions that I will write as phi 0 for the ground state of a single particle system, phi 1, phi 2, etc. Now the labeling of 0, 1, 2 is somewhat arbitrary. And for the hydrogen atom, we would actually call the ground state n equals 1. But since it's just a label, I'm just going to call it 0. And E0 is going to be less than E1, is going to be less than E2, etc. And so just to draw a picture, so let's say my potential V of R looks like this, sort of schematically. This is my radial coordinate. And then I can have one wave function would be the ground state. We know from the variational principle that it might look something like that. So that's phi 0. And then phi 1 might look like something like that. And the wave function for phi 2 might look like who knows, something like that. Okay, so we're not being specific about them. We're just saying that they're ordered in energy, though. And we're going to pretend they don't interact with each other. So we're going to treat that later as a perturbation, or imagine treating it later as a perturbation. So pretend particles only interact with a potential and not with each other. And let's try to enumerate the total energy eigenstates. So let's go back to n equals 2 for the moment and consider n equals 2 bosons. Okay, and so what's the wave function of the ground state going to look like? It's just going to be the product of the two lowest energy eigenstates I can find for the individual particles, which is phi 0 R1 and phi 0 R2. And I don't need a square root of 2 because they're the same. And this is going to have symmetrized a symmetrized spin wave function, because already the spatial part is symmetric. Now, if it's a spin 0 boson, then of course I don't have to worry about spin at all. But if it's spin 1 or spin 2, then I should make a symmetric combination when I do the addition of the spin angular momentum. Okay, and the energy of this, because we're ignoring the interaction between the particles, is just, I should have maybe called these curly E's to remind us that they are unperturbed states. So this is 2 curly E0. Okay, now consider n equals 2 fermions. Okay, then I can do exactly the same thing. Okay, my wave function is just the product of these two individual wave functions. And why can I get away with that? Because that's symmetric, but I can get away with it because I can assume that the spin state is antisymmetric. So with antisymmetric spin state. And so when we did the helium atom before, that was what we were really assuming. We just wrote down this when we did, for example, our variational principle. We did it also when we did first order perturbation theory for the helium atom. And in both cases, what we were really assuming is that of the 4 possible spin states that the helium atom could have, it was choosing to be in the antisymmetric s equals 0 spin state. And then once that's true, I can just sort of ignore the spin and just do the variational principle on this part. Now that was for the ground state, because we're talking about only the ground state when we write down this energy. And so next time when we reconsider this for the excited states, we will not be able to assume that it's antisymmetric in the spin. Okay, but so this also has total energy twice curly E0. And then if you want the real energy, you have to apply perturbation theory on top of that. Okay, so now let's add more particles of the same type, whether they're fermions or bosons. Okay, and so for n bosons, what's our wave function going to look like? Okay, first of all, it's going to be a function of
I'm sorry,
n
Professor.
different coordinates.
Could you scroll up just a little bit, please? Thank you.
Okay, so this is going to be just the product. So again, I'm just writing down the ground state. So I'm choosing all of my individual wave functions to be the lowest thing, the lowest energies that they can possibly be. Okay, and now let's say, okay, we multiplied that to get the wave function. What about the spin state? Okay, and the spin state, again, I don't know what my pen's doing here. So my spin state has to be totally symmetric. So what you have to do is, well, for spin 0, it doesn't matter. That's automatically symmetric. But if it's spin 1, I need to add spin 1 with addition of angular momentum together n times. And then of those states, I need to look at the totally symmetric part, which I can do by looking at what happens when I interchange the different spin components and pick out the totally symmetric part. But I can do that, and the energy will be just n times the individual unperturbed energies. Now here's where things get different though. For n fermions, you can have at most 2 spins. Let's say they're spin 1/2 in a totally antisymmetric state. And so the way you can realize that is just because if I look at the z components of them, there's only 2 possibilities. It's up or down. And if I have 3 of those, then I can have one of them up and one of them down, but then the third one can't be either one because it's got to be anti-symmetrized. Okay, so if I'm going to find the ground state energy, 2 fermions can be chosen to have the state phi0, and they will necessarily be in a spin 0 state. And then 2 more can go into the next excited state, and they also will have spin 0, etc., up to I can have phi n over 2 if n is even, or I can have phi n plus 1 over 2 if n is odd. Okay, and then I add up to find the total energy of the ground state. I add up all the individual unperturbed energies of those. And so I'm going to get 2 curly E0 plus 2 curly E1 plus etc. plus 2 curly E n over 2. That's if n is even. And I get almost the same thing. Okay, except I get 2 curly E n minus 1 over 2. And then I have 1 left over, which can be curly E n plus 1 over 2. Okay, and that's for odd n. Okay, so that leads to the shell theory for atoms. Because in atoms, what we're doing is we're combining identical electrons. So each unperturbed energy level can have exactly 2 and no more electron states, because now I'm including the spin. And so neglecting for the moment the small, because it's multiplied by the fine structure constant, fine and hyperfine interactions or splittings. Oops. The level E sub NL, I guess I should call it curly E, can have up to 2 times 2L plus 1 electrons in it. The 2L plus 1 is because the M sub L can take on that many values, and the 2 is because of this spin that we've been talking about. Okay, so we will be talking much more about the energy levels for N electron atoms. We'll do helium again one more time next time, and then we'll graduate to multi-electron atoms. All right, any questions about that? All right, so the other thing is that we have a midterm coming up on next Monday. So on the course webpage, I put the rules for the midterm. Let me share the screen for that. You can download the same thing that I'm about to share from the webpage. Again, many of you have, most of you have taken exams in this course before, but let me just go over it very quickly. So it's going to be, and I have to confirm this, but it should be in Davis Hall 121. I believe you're still required to wear masks in buildings at all times. You should bring something to write with and something to erase with. I decided you can bring 2 sheets of paper with anything you want in your own original handwriting, and you can use front and back of both sheets so that you don't have to cramp your writing style. But again, it does have to be your own original handwriting. You can't photocopy. You have to write it yourself. If you like your favorite paper to write on, to turn in, I encourage you to do that. But please do make sure that the paper that you turn in has no loose edges. I'm not going to mention any names, but on a previous exam, one of your exams had a bunch of fuzzy loose edges and ended up jamming the scanner in the main office for a half hour. So don't do that. So you can bring paper, but try to make sure that it's scanner friendly paper. No books, the course notes are not allowed, no calculators, no electronic devices. You do not have to write down the vector and coordinate identity formulas for things like curls, and you don't need curls anyway, but Laplacians and things like that. That will be provided for you. You can also use my blank paper if you choose to use my blank paper. And then lastly, what to study. This test will not cover this identical particle things that we've been talking about for the last few lectures. Instead, it will cover time-independent perturbation theory and the variational principle, which is basically what we've mostly covered in the first 5 homework sets and their applications. So I urge you to study homework problems and the concepts that they involve. This is probably not the time to start going through the notes and reading the notes carefully, because you don't have time to spend on that. And so when you're making your formula sheet, if you're wondering, what should I put on my formula sheet? For a good first pass through, what you should do is go through each homework problem. Think of what formulas did I need for that homework problem that I don't have memorized. And then those should be the first things that go on your formula sheet. And then you should ask yourself questions like, what sneaky thing can Professor Martin ask that tests the same concepts or other aspects of time-independent perturbation theory and the variational principle that might be variations on these questions, and then write those formulas on your formula sheet. So that's the strategy that I would employ, at least. Okay, any questions about the midterm?
Professor, so could you please clarify exactly which homework assignments are covered in the midterm? Is it like the first
Oh, good.
three?
So everything that we've had up till now. And so, by the way, on Friday, your last homework set is due on Thursday. And so on Friday afternoon, sometime, I will be emailing everyone the solutions to that homework. And so there won't be as much well, you can't turn it in after the solutions go out on Friday. So that would be late anyway, but so basically it's anything on the first 5 homework sets. Good, other questions?
I think I'm good. Thank you.
All right, so if not, then I will see you all on Friday.
Professor, can I see the main page again? I still had 2 more lines to write.
Sure. Should show up in a second, hopefully.
That's an extra odd there, correct?
Yeah, that's an extra odd. Very good.
Yeah, Professor, one last thing. I may be mistaken. I thought last week or last session, I think it was last week though, I thought I heard you say that because of the midterm, the deadline of the homework would be extended. Was I mistaken?
Yeah, I think that's sort of the opposite. The fact that there's a midterm means that I can't accept late.
Oh, okay. Okay, well, I misunderstood. All right. Thank you
Okay.
so much.
All right.
Goodbye.
Okay, bye.